So I will introduce.
Yes.
So it is my pleasure to introduce today's speaker, Danfeng Yao. Danfeng got her undergraduate degree from Beijing University, one of the best institutions in China. She has 2 master's degrees, one from Indiana University and one from Princeton University. She's currently a 5th-year PhD student in Brown University, and she's working with Professor Roberto Tamasia. She spent the summer on an internship in HP Labs in New Jersey, working with Stuart Haber and Tomasz Sander and their group.
Bill Horn, he's a manager.
Yes, and their group. And her talk today is about the verification of integrity for outsourced content publishing and database queries. Danfeng.
Yeah. Thank you, Mike, for the introduction. So this is my summer intern work at HP Princeton, and the group is part of a Trusted Systems Lab. All right. So I'll first start with motivations for data integrity, and I'll describe our models for outsourced computing, and then I will talk about our 2 contributions. One is the verification of third-party pseudonymized documents. The other is the verification of aggregate query results. And HP is very much into outsourcing business, and outsource is a kind of an overloaded term, and here I mean that HP is managing data and IT infrastructure and other computing resources for its clients. And here is just a list of some of its clients. And this outsourcing is a billion-dollar business for HP. For example, for Procter & Gamble, it's multi-billion-dollar over 5 to 10 years. And the outsourcing usually multifaceted, so not only just the data, but also IT infrastructure, business services, and computing supports. For example, for Canadian Bank, HP is actually managing the ATM machines for the Canadian Bank, and also branch tellers, and also fraud detection systems. So it's all kinds of computing systems. And the model that we consider specifically is shown here. It consists of 3 parties. One is the data owner. The other is the service provider. We also call it the middleman, which is the role of HP. And the users are clients of the data owner. So it can be the people at Canadian and at Canada want to get money from the Canadian bank. So the data owner gives the data to the service provider, and service provider not only disseminate the data to the users, but also need to do some kind of transformation based on the user's requests. And this kind of transformation will change the presentation of the data. So then the next question is, how does the user know the data obtained from the service provider is authentic, is trustworthy? So in our trust model, we consider that the user will trust the data owner, but the user does not necessarily have to trust the service provider. So the user doesn't actually have to know anything about the service provider, the middleman. The user only have to trust the data owner and its public key, and then that is used to verify the information obtained. So this is our basic model. Now, just here is an example of what kind of transformation that we consider. And this is a redaction transformation. The digital redaction is essentially remove parts of a document. And the removed parts may be sensitive or may be unauthorized by the user, depends on the user's permissions. In recent years, a lot of government documents are declassified. So, for example, this is a military document about the Iraqi war, and you can see parts of the document. For example, the number of divisions at the bottom of the page are blackened out. And once the user obtains this kind of redacted document, how does the user make sure that this is authentic redacted version of the original one. So this is one type of transformation. And then interesting to mention is that recent years there are a couple of public scandal about redaction, is because a lot of people think redaction, they just copy a black ink on top of the original document, but that is not enough. So AT&T and some other organizations, they release redacted document. However, the public can copy it, copy the blackened text, and then paste it into a notepad, and then see the original text. So Homeland Security actually released a 13-page document titled Redaction with Confidence to tell people how to work with Microsoft Word to transform a redacted document in a PDF form. Of course, this talk is not about how to do that kind of transformation. All right, so this is an example of another kind of transformation. It is actually a database query. Suppose the data owner gives a database to the service provider and asks the service provider to manage the database and answering queries from the users. Now, for example, the user can ask all kinds of database queries, like average salary of the employees. Now, the user only get back the 70K as a result. How does the user verify this is correctly computed? Now, if you think about this, you may ask, why just give all the database to the user? However, this may not be applicable in some problems. For example, in medical scenarios, medical records are highly sensitive information. They contain personal records. So even though the public can query the statistic of the data, the public may not be allowed to get hold of the actual individual data entries. So in that case, there is this privacy issue and how to verify the integrity of the result considering this privacy issue. Okay, then why do we care about data integrity? Data integrity, in the most common sense, you can think about adversaries may tamper with the outsourced data and then tamper with the computing facilities hosted by the service provider. So that is pictured in the lower part of this slide. When the user gets a tampered result, the user should be able to be aware of it. Besides that, the service provider also want to use this integrity proof as a tool to prove to a third-party auditor that it is compliant of certain regulations and specifications. So that's why we care about data integrity in a general sense. Now, as I told you, data integrity can be challenging, and one reason can be because of privacy issues. The user has to prove the obtained result without actually knowing the input of the computation. And that is one challenge to this problem. And we also consider efficiency issues. Efficiency issues is that we don't want the data owner to take active participation into proving the integrity. Because in the most straightforward solution, you can basically say, okay, data owner, you sign every query results that the user asks. Then the data owner has to be online all the time, answer the digital signatures. And of course, conventional digital signature is no longer valid in this scenario. As I said, data, like the redacted document, they undergo transformations. If you just sign the original document using RSA signature, they will not be valid at the end after parts of it are removed. So we'll have to use some other techniques So in this talk, we only consider two aspects of the outsourced verification problems. And one of it is verification of third-party pseudonymized document. And this is very close to redacted document. In the redaction case, text is completely removed, and we want to provide a pseudonym instead of a blackened text. A pseudonym example in this case will be, we'll say, soldiers in A division and B division have come to refer to the certain thing. And the good thing about pseudonym is it provides a better reading context for the readers, and also pseudonym can be linked. For identical words that appeared in the document, they will replaced by identical pseudonyms. Therefore, the user have a better reading context. And another aspect that we consider is integrity verification of third-party aggregate query results. And aggregate queries include sum, max, min, count, average. And we consider privacy-preserving verification of both the correctness and the completeness of aggregate query results. I'll give more explanation in the later part of the talk. All right. For the pseudonymized model, we consider again three parties. We have a data owner who has a document, a service provider who will pseudonymize the document, and the user who queries the pseudonymized document. So the data owner will first prepare the document by signing it and provide some auxiliary information. And this is given to the service provider in a secure channel. Now, once the user requests for a pseudonymized document, the service provider will pseudonymize parts of it based on the user's permission. Now, how to determine who can access what part of the document is outside the scope of this talk. So we just say the service provider prepare a pseudonymized document according to some specifications. And then the user verify this document with the public key of the data owner. Now the user does not need to trust the service provider in this scenario. So the security requirements, we have three security requirements. One is confidentiality. That is, having seen the pseudonyms, the user cannot guess with non-negligible chance of the original context. So this is provide the secrecy of the document. The other is unforgeability. Essentially, it says service provider and any other third party cannot forge a valid signature that can be accepted by the user. And then finally, consistency is specific requirement to this scenario. Consistency basically means identical words in the document has to be replaced by identical pseudonyms. So the user will get the original context of the document. So those are the three security requirements. And then we also give a formal definition of this based on a semantic secure model, but I'm not going to talk about this in this talk. All right, so our solution is based on Merkle hash tree, and we generalize an existing redactable signature scheme by Johnson, Mona, Song, and Wagner in 2002. So here I'm going to first briefly describe their solution and then talk about how we generalize their model to pseudonyms. So imagine you have a very simple document, just have 4 words. And each word is a subdocument, is a component of the document. Now, we want to construct a Merkle hash tree. The data owner constructs a Merkle hash tree based on the document, and then eventually sign the root hash, which will be used as a proof for the user to verify the integrity later on. The data owner uses random values when computing the Merkle hash tree. So for each component of the document, a random value is introduced, and they are hashed together with the text, and a Merkle hash tree is constructed from the bottom up. So the reason that we use this random value is to prevent a dictionary attack. Because if you omit the random value, once the user has the hash value, for example, H00, the user basically can go through all the combinations of words and then see whether they match with the hash value. So we introduce this random aspect. And then the root hash is signed by the data owner. And all these information, including the random values, are given to the service provider. So the service provider will know the original context. Will have the original text and the random values, and also the digital signatures. So for the redaction option, for example, if we want to redact fox, that means we want to remove the fox away from the document. Now, the service provider will have to do the following. We'll have to compute intermediate hash for fox. And that is H11, which is computed the concatenation of fox and its corresponding random value. And H11 is computed because when the user will have to reconstruct the Merkle hash tree later on. So without knowing fox, the user can still use H11 to reconstruct the tree and the root hash. So the redacted document, and the redaction is represented by the black square, along with the random value. Notice that for non-redacted document, random values are given to the user. For the redacted part, the random value is omitted. In replace of that, the intermediate hash is given to the user. Now, for verifying this redacted document, the user will have to do the following. The central idea is to basically reconstruct the root hash from this redacted document. And for the parts that are redacted, the user does not know the leaf nodes of the tree, the user will use the intermediate hash, H11. So it's quite straightforward. And once the user gets the root hash, the signature is verified. So this is the original digital redaction signature scheme. Now we want to generalize this to consider pseudonyms. And we actually just made a very simple modification to this. So here it is. We ask the data owner to choose pseudonyms during setup. At the beginning of time, the data owner will decide, okay, for parts of the document that will potentially get pseudonymized, I want to choose the following pseudonym for them. So for example, the data owner will choose Sam to replace Fox. And then Merkle hash tree will be constructed in a similar fashion, but the pseudonym will be hashed together. So we not only hash the Fox and the random values, we'll also hash the Sam, the pseudonym. And for the parts that will not be pseudonymized, it will be computed the same. We construct the root hash, sign the root hash, and then give everything to the service provider in addition to the pseudonym. Now the service provider will have to pseudonymize Fox with Sam essentially what it does is compute H11 just as before, and then give the pseudonymized document, replace Fox with Sam, and then give the rest of the information to the user. Now the following verification is just the same as before. The only difference it's a minor difference. So the user will has to hash H11, the intermediate hash, along with the pseudonyms in order to construct a root hash. Now, so how does this satisfy all our three requirements? Consistency, it is pretty simple because we now ask the data owner to choose the pseudonyms. So we trust the data owner to choose consistent pseudonyms at the beginning of time. And for confidentiality, which means that once you see the pseudonym, you cannot guess the original text. And that is satisfied because the pseudonyms are chosen by the data owner independent of the original text. It is sort of random chosen, so there is no connection between the pseudonym and the original text. And for unforgeability, it essentially boils down to the digital signature scheme just as before. So this is very simple pseudonym protocol. However, there is one thing, is one constraint, that is the service provider will always has to wait for the data owner to choose the pseudonyms. What if the service provider wants to choose pseudonyms on the fly by its own? So then we have even simpler scheme that actually achieve this. So we have what is called ad hoc pseudonymization protocol that allow the service provider to choose pseudonyms independent of the data owner. So we observe this. So imagine you have a very short document, consists of 4 words, A, B, C, A. Now A are identical. I couldn't think of any short sentence that makes sense and also have repeated words. So we'll just use letters to represent this. So now for each word, we choose a random value. But notice that for the identical words A, we choose the same random value. Now this means what? When you compute the hash value, for both the first one and the last one, they will have the same hash value, H00. And then the data owner will do the construction of Merkle hash tree just as before. Now in this protocol, we'll use the hash value H00 as a pseudonym. So now the consistency is satisfied because identical words will have identical pseudonyms, and the confidentiality and the forgeability will just as the same, can be proved as before. We also extend this to allow the service provider to compute an arbitrary pseudonym from the hash value. And that is based on a symmetric key encryption scheme, actually. So essentially, the service provider can just get the Merkle hash tree and then choose whatever pseudonyms he wants to have to replace the parts of the document, independent of the data owner. And how this is done is omitted here. If you're interested, I can find more information about this for you. So essentially, in this part of the work, we have verification of pseudonymized document that is pseudonymized by a third party, but the verification is independent of the person that performed the pseudonymization. So next, we move on to the second part of the talk. It's about verification of aggregate queries. By the way, if you have any questions, just feel free to ask. Yes?
Just a quick question. So the pseudonymization, it applies to single words. What about if you have a large paragraph that's been blanked out? Are you going to have 40 pseudonyms
Right.
within that paragraph, or is it just going to be?
So it depends. So the granularity of components of the document depends on specific applications. It can be a sentence, can be a word. So if the data owner decides the granularity is a word, then yes, you have to have multiple pseudonyms. Of course, the data owner can say this part of paragraph will have a sentence as a basic component, and then for that paragraph, we'll have word as a basic component. So depend on specific application. I forgot to mention this. Yep.
Based on what you were showing us, I was wondering if you've had issues with possibly dealing with maybe the same word with lower and uppercase letters. I mean, if you're looking at a document from that standpoint, because if you're computing the hash based on the ASCII, the ASCII values are different. Therefore,
will be different. Yeah, that actually is a very good point. We haven't considered that. That's true. It will in that case it will have a different pseudonyms, and that's a very good point. We'll have to think a little bit more about that. All right, we'll move on. And in this model, verification of aggregate queries on outsourced database, we have basically three parties again. The data owner this time delegates a database to the service provider, and the users will make database queries. And in this case, we focus on aggregate queries because it is quite challenging. Once you have the aggregate result, you may not necessarily know how to compute how to verify the correctness of the computation. And our model actually is quite general. It also applies for non-aggregate queries such as select, join, project. But we're not going to cover that in this talk. So here is a simple example of what kind of query that we consider. Suppose you have two attribute database table, age and salary. The query is sum all the salaries that are above 60K. So the first, third, and the last record are selected, and then the sum is computed. Now, by correctness, we mean that whether the sum 215 is correctly computed. Now, again, we consider privacy. We don't want to give the user the inputs, 65, 70, 80, are hidden from the user. This is for correctness. For completeness, we consider the selection part. So you have a selection clause that is salary above 60K. Whether the numbers that are computed in the sum satisfy the selection criteria, whether or not the non-selected entries violate the selection criteria. So in this case, we have to prove that 50K is less than 60K. So it does not satisfy the selection criteria. And again, we don't want to give 50K that value to the user. So the user basically has to verify without seeing 50K. So this is simple query. And we also consider more expressive queries. For example, nested query. You want to compute an average first for a certain group of people, and then compute a max. So this kind of nested query will be quite commonly used in database systems, and how to verify the correctness and the completeness for those queries. And also for selection, we want to also consider multi-attribute selections. Not only just one attribute, but multi-attributes. All right, so here will be some basic building blocks that we used. And this is a commitment scheme. Commitment scheme is very commonly used, for example, in contract signing, optimistic exchange. It has two operations. So one is commit, the other is open. The data owner has a value X. At the beginning, the data owner does not want to. So the X is secret to the data owner. So the data owner will compute a commitment of X, and this usually makes use of a random value, R. The commitment is given to the user. The user may do some operation based on the commitment. And later on, the data owner can open the commitment by revealing X and R. The user can compare whether the previous commitment is correctly computed based on X and R. So if you think of an analogy of this, so basically without open, a commitment is useless because the user cannot verify it is correct or not. So analogy of this is sort of, if you think of commitment is like an engagement and the open is like a wedding. So without the wedding, the engagement is kind of useless. And you have to have both parts of it in the system in order to verify certain number is correctly computed. And what we use is two properties of a commitment. One is hiding, the other is binding. Hiding is once you see a commitment, you cannot guess the value that is committed. Once you see C, you cannot guess X. And the binding means a commitment can only be opened to one value. So this is a commitment scheme. And we actually use the Peterson commitment scheme, which is a specific kind of commitment scheme. It has this nice property of a linear homomorphism. Essentially, it means commitments, the product of two commitments equal to the commitment of the sum. So it's highlighted in the green formula. So essentially, a user can compute a commitment of something without even knowing what it is. And the rest of it is just some details. We will not cover it here. Now, here we have a quite complex data structure that we use to bookkeeping the values, the commitments, and the indexes. And here I'm going to tell you the data structure in the most general form. And then later on, when I dive into the detailed examples, we'll actually use a very simple data structure. But here, if you consider a database table that only have two attributes, the data owner will maintain a database table that has actually 4 extra columns. The middle ones are commitments of each individual values. Okay, and the last 2 columns are indexes. Indexes representing the sorting of the each data entries, and their indexes in the sorted list are kept. So you can see the age is sorted already, so the index is 1, 2, 3, 4. Now, the database owner will construct a Merkle hash tree just as before, but this Merkle hash tree will have a lot more contents. For each row, the plain text value, commitments, and the index are hashed together. And this is done for each row, and the root hash is computed. So the indexes, so the last 2 columns are used here for us to prove the completeness property of a certain query. So essentially, it will be clear later on, but you can think about if the data is sorted based on certain attributes, and then you can prove to the user that the elements that are out of the range is greater than the selected component or lower than the selected component. So you can use a sorted list to prove the completeness quite easily. And those indexes are used for that. Now the root hash is again signed by the data owner, and this information, all the table, all the entries in the table and the signature are given to the service provider. Okay. So I'll talk about how to do sum verification and also how to do max. And for those, for example, average and count, it is based on sum. So once you know how to do sum, you can do those. And the min and max can be done in a similar fashion. So the basic idea is the database owner commit to each individual data entries and then sign the root hash of the commitments. And the user will obtain a query results and also use the commitments and the signature to verify the correctness of the query. Now again, we're going to use the homomorphic property of a commitment scheme, which will be clear in a minute. So consider a very simple database that has one attribute, 4 data record. The data owner will make the commitments and assign the hash of the commitments, give all these information to the middleman. Now the user query for the sum of all the data record. The service provider will compute the sum using the plain text data and then give the sum, the commitment, the signature, and the random value R to the user. The random value R is used to open the commitment of the sum. So what the user do is go through this 3-step verification algorithm. First is to compute the commitment of the sum. Notice that using homomorphism property, the user doesn't have to know each individual value in order to get the commitment of the sum. It will just compute the product of all the commitments. And then verify the commitment is truly corresponding bind to the sum by using R to open it. So the user knows 265, knows R, and open the commitment. And then finally, the user will verify the signature for all the commitments. And the signature is used to authenticate the commitments, because without the signature, anyone can compute the commitments, and the user will not be able to tell whether it's a commitment of the original value or something completely made up. All right. So this is a sum verification. Now, for the max verification, we'll have to use an additional building block, which is called the zero-knowledge proof of a greater than relation. So the purpose is to prove two numbers are, one number is greater than the other without actually revealing both of them. So for example, you have a prover that has two numbers, 5 and 10. The verifier eventually will get a proof that says that commitment of the first number and the commitment of the second number will satisfy the relationship, the inequality shown here. So the prover will first generate the commitments, and then the user will submit a challenge, and then the prover will have to generate a proof based on the challenge to show that two numbers are satisfy this relation. So this will be used as a building block to prove comparison-based query results and also to prove completeness. All right. So for max verification protocol, the setup is exactly the same as before. The data owner generate commitments, send the commitment. Now, if the query is a max of all the salary, 80 is returned, along with the commitments, the signature, and also R. So the user will have to verify 80 is actually greater than or equal to the rest of the data entries. And to do this, the user will essentially go through multiple zero-knowledge proof to to get the assurance that 80 is greater than each individual data elements. And this proof has to be carried out between the user and the service provider. And it has so there are interactive proof protocols. That means the service provider has to be online and have to engage in the challenge response process. And there are also corresponding signature schemes. So essentially, the service provider will compute the proof once and for all, and then give it to the user for verification. So as you can see, without actually knowing the inputs, the user will be able to verify the query result. Again, this protocol does not reveal, does not try to hide the query results themselves. So if the user queried the max, the user will get the max. So this is a sort of a general property of all the privacy-preserving protocols. You cannot hide the user from knowing anything. And also the user will be able to infer something. For example, the user will know, okay, the others will be less than 80. And that kind of inference knowledge we cannot prevent the user from gaining. So now for the completeness verification, I'm going to present it in 3 examples. The first one is very simple. Again, completeness means that the queries that are selected are the complete set of the selection. Those are not selected must have violate the selection clause one way or the other. So if you think about a very simple query, average age of employees who are younger than 37, now you have 4 data entries. The last one is older than 37, so that is not selected. To prove the completeness, what you can do is just to show that the value that are committed in the last data entry is greater than 37, without even revealing what the value is. And then the rest of them are aggregated together. So this is a simple example, only has one attribute. If there are multiple attributes, how do we do? Consider this. If the selection is done on the age, but the aggregation is done on the salary, we can essentially do the same thing. We'll aggregate the salary and then prove that the last entry is beyond the selection range. Then for a more complex case, we want to do a selection over salary and aggregation over salary. However, the salary is not, the way that Merkle hash tree is arranged does not corresponding to the sorting order of the salary. So you can see that C65, C50, C70, and C80, they corresponding to the commitments of the salary, and they are out of order. So that's why we use the index. In this case, we'll have the index of the relative ranking of this data record hashed together in the Merkle hash tree. And then in this case, we can prove that the last data entry 80 is beyond the selection range, and then 80 is the immediate element that beyond the selected element. So the 80 is just the next element greater than 70. And this is proven by showing that the index of 80 is greater than the index of 70. So you show the order by proving the index. And then we can use the zero knowledge proof of greater than relation again. So you can prove the order of index without actually revealing them. All All right. Any questions, concerns? No. So essentially, this is the way that completeness is proven here, and you can see we can handle quite complex queries. We consider multiple attribute queries, and essentially we can also generalize this to nested queries. If you consider max over average, you just go through the average proof as we've shown here, and then you have the commitment of average results, and then based on those we can carry out another round of proof for the max. Okay. So
Can I ask a question?
yep.
Could you go back to the slide where you have the zero knowledge proof for the max?
Okay.
So, if I understand this correctly, then when you send the commitments at the end, those aren't multiplications in step 5, right?
You mean at the end?
Yeah. So what you're not only disclosing the maximum, but you're also disclosing how many elements are in the table to begin with.
Right. The user will know how many people in the database record. Yes.
So it's not really zero knowledge. It's it's not revealing a lot of information, but this could be useful, especially if you use that with other things. Like before, you're trying to show the index numbers were not bigger and hide that information. And it's quite possible I could use this information over a series of queries to figure that out.
Oh, well, I think I understand your question, but let me clarify it. So as you can see, that the commitments values are actually reused, and the model does not actually. The current model, we do not aim to solve this what we call unlinkability issue. So essentially, once the user submit another query, if, for example, the commitments of 65 will get back to the user again, the user will have some knowledge of this particular data entry, even though the user does not know it is 65, but the user knows it appears in multiple queries. So for example, if you say, give me the employee who satisfy a certain selection criteria, and then you selected another query based on another selection criteria, and this data record is returned multiple times, you will know that it will satisfy, it actually has certain intersection property. So for those, we do not prevent, our solution does not prevent those kind of linking attack. But I'm not sure is that what you asked, or you asked something else?
Well, it sort of answers the question, I think.
All right.
And then just another slightly technical question, but what's your zero knowledge model then? Does the proof of security go through with concurrency, or is it just the cone of silence model, or?
It used a general zero knowledge proof protocol. So essentially, the proof is based on the simulation. The adversary. So basically, we can simulate the transaction of the zero knowledge proof, even though you don't know anything about it.
It's the traditional Goldwasser-Macaulay-Rakoff definition of zero knowledge?
Yes.
Okay, thanks.
All right. All right. We're almost done. For the related work, redactable signatures has been studied quite well recently. There are several solutions both on Merkle hash trees and aggregate signatures. Verification of outsourced databases are extensively studied recently. And for non-aggregate queries, a lot of studies is based on context where the user will obtain the clear text document. There's also a very large number of work on aggregate queries on encrypted data. And for those model, the data owner will encrypt the data using its own key. And actually, the user will the data that the service provider hosts can only be queried by the data owner itself. So our model is slightly is different from theirs. We allow anyone to query the outsourced data. And also there's a lot of work on data generalization using methods to hide parts of the data so that the user's privacy is protected. So for conclusion, we have a general model and several techniques to prove data integrity in this outsourced model. And these solutions have potential applications in third-party auditing services and proof of compliance. And in our technical reports, we give formal security definition and the proof of security. And there are a couple of open problems, as I mentioned earlier. In response to the IU's question, the linkability is one thing that we want to solve. Essentially, when the users issue multiple queries and the same commitments are returned, the user will figure out something. So one solution is to think about re-randomize the commitments, but that will involve the data owner to re-sign the new commitments. So that's one thing that we want to solve in the future. And also, in general, we want to improve the efficiency because right now the verification is linear in the sum and the max verification. All right, so that's it. Any questions?
I have a question.
Yeah.
When the root hashes don't match, do the schemes generally provide a way to pinpoint where the root cause of it is, at which spot it is in the document?
No.
It just tells you yes or no.
Right. You cannot tell. There's no way of telling because root hash is the only hash value the user has. So it can be anywhere. Right. Yeah. Yeah. It would be interesting to pinpoint the place that someone has tampered with. Yep.
Any other questions? Let's thank the speaker.